Hello and welcome to today's ACM SIGSOFT webinar. This webcast is part of ACM SIGSOFT's commitment to provide value to its current and future members. The ACM SIGSOFT webinar series features speakers from the Future of Software Engineering track at the International Conference of Software Engineering, as well as select keynote speakers and distinguished paper authors. I am Robert Dyer, Assistant Professor at Bowling Green State University, and it is my pleasure to welcome you today. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. First, the slides will advance automatically throughout the event. On the bottom panel, you will find a number of additional widgets and resources. If you're experiencing problems with the slides or audio, press the F5 key in Windows, Command R if you're on a Mac, or refresh your browser on a mobile device. Or you can close and relaunch the presentation. To control volume, adjust the master volume on your computer. At the end of our presentation, we will have time for questions. Please type your questions into the Q&A box at any time during the webinar, and then click the Submit button. This session is being recorded and will be archived. You will receive an automatic email notification when it becomes available. Today's presentation is Probabilistic Programming, Algorithms, Applications, and Synthesis. Our speaker today is Aditya Nori from Microsoft Research. Aditya is a member of the Programming Languages and Tools group at Microsoft Research India. Over the past few years, he has worked on exploring various synergies between programming languages and machine learning, including the use of machine learning techniques for proving program correctness, specification inference via Bayesian analysis, probabilistic programming via program analysis, and productivity tools for machine learning tasks. He was awarded the Distinguished Paper Award at FSE 2006. Aditya, we look forward to your presentation today.
Thank you, Robert, for the introduction, and hello, everyone. I'm going to talk about probabilistic programming, an exciting area that lies in the intersection of machine learning and programming languages. Specifically, I will talk about three topics. The first is about program analysis techniques for solving probabilistic programs. The second is an interesting application of probabilistic programming that I've been working on for the past year or so. And finally, the third is an approach for automatically synthesizing probabilistic programs. This is joint work with a number of wonderful students and colleagues that I've had the privilege of working with over the past few years. So let's get started. So as we all know, data is everywhere and manifests in various forms. For instance, to name a few data sources, there are more than 5 billion people calling, texting, tweeting, and browsing websites on their mobile phones. Facebook has more than 901 million active users generating social interaction data, and there are approximately 340 million tweets that are sent every day. So consequently, developers increasingly have to reason about data as well as code. We see that today's software involves data analysis. We also see that developers increasingly are employing machine learning models in their software, and that they need to deal with data that is fairly incomplete, noisy, and approximate. So given this state of the world, what are the new programming language challenges? We think that there are two main challenges. The first is that of data acquisition and manipulation. With lots of data in the world and occurring in a zillion formats, conversion to one's own favorite format and manipulating the data is a very time-consuming and error-prone process. One of the main problems here is that there is a large mismatch between data in the world and programming languages. Specifically, there are poor facilities in programming languages to implement data transformations. The second challenge is how to reason over data. For this, programs need to naturally deal with machine learning, statistical, and approximate computations. Unfortunately, at the moment, good abstractions for these kinds of computations are virtually non-existent. So in today's talk, we will discuss this aspect, which is about programming abstractions for reasoning with data and applications. In particular, we will focus on probabilistic programs. I will first give a quick introduction to probabilistic programs. Then I will show you that inference for these programs can be done using well-known techniques from the area of program analysis. As many of you would know, there are a number of interesting applications of probabilistic models and programs, In this talk, I will show you how probabilistic programs can be used to debug machine learning classifiers. And finally, I will talk about how to automatically synthesize probabilistic programs. So let's get started. Probabilistic programs are usual programs written in languages such as C, C#, Java, Lisp, or Scheme with two additional constructs. The first is a probabilistic assignment statement that allows us to sample from various distributions. And the second is an observe statement that allows us to condition values of variables. And the goal of a probabilistic program is to succinctly specify a probability distribution. So why do we want to write probabilistic programs? This is because they provide an abstraction layer that hides the complexity of sophisticated inference techniques, which also means that they can enable fast experimentation with machine learning or statistical models. So here is an example of a very simple probabilistic program. As you can see, this program has two Boolean variables, C1 and C2. C1 gets its value true or false from a fair coin toss or a Bernoulli distribution with mean 0.5. Similarly, C2 gets its value from another coin toss. Finally, this program returns the tuple C1, C2, and the meaning of this program is the distribution over this return expression C1, C2. Specifically, it is this table shown in the slide, and it is easy to see that the joint distribution of C1, C2 is the uniform distribution over the four choices shown in the table. Here's another example. This is the same program as before, with the difference that there is an observe statement after the sample statements. This observe statement is analogous to an assume statement that is quite popular in program verification. Essentially, the observe statement blocks all runs of the program that do not satisfy the predicate specified by it. In other words, this program does not admit the value C1 equals false and C2 equals false. Therefore, the meaning of this program is given by this table shown over here in this slide, with the state C1 equals false and C2 equals false being assigned probability 0, and all other values are appropriately renormalized so that the table is a valid probability distribution. Here is another example of a probabilistic program with a loop. The loop over here iterates until the predicate C1 or C2 is satisfied. Now, if you look at this closely, this sounds very similar to the program that you saw in the earlier slide, which is shown below. Essentially, the while loop is simulating an observe statement, and therefore both these programs represent exactly the same probability distribution, which is shown by the table over here, which is the uniform distribution with parameter 1/3. And finally, here's another interesting program with a loop. It has two Boolean variables, B and C. And within the loop, the value of B keeps getting flipped until C gets a value false. And the meaning of this program is the distribution over B, because we return B, and is given by the table shown to the right. And the probability of B taking the value true is given by the probability of the loop in the program executing an even number of times. And that is given by evaluating the geometric series shown below, which basically says that the probability that B equals true is equal to 2/3. Let's look at a real world example. Suppose you'd like to estimate how good you are at playing Halo. Why do we need to know this? There are millions of Xbox Live games played every day, and there's a need to match players of similar skills to keep games interesting. And this is implemented in Xbox by a system called TrueSkill. And the original TrueSkill inference algorithm from MSR Cambridge was months of work and hundreds of lines of code. Let's see how this can be done succinctly using a probabilistic program. So at any time, a set of skills is maintained for every player, and each game that is played results in a performance ranking. We want to use that performance ranking to adjust our estimates of the skill levels. For instance, over here, we have a game with 3 players, Sully, Sniper Eye, and Dr. Slowplay, where Sully is the winner with the highest score of 25. And we would like to estimate the new skills of the players after this game is over, given their old skills. So let's assume that the skill for each player is stored as a random variable satisfying a Gaussian distribution. So essentially what this says is that the more the games that are played, the more certain we are of a player's skill. So in this figure, as you can see, Sully has a very wide uncertainty, and it's probably the case that Sully is a newish player. On the other hand, Sniper Eye has a narrow uncertainty, and therefore would have been a very experienced player and would have been in the system for a very long time. So since in the match we see that Sully beats both players, his skills gets quickly promoted to a higher value, but as you can see from the width of the curve, it is still quite uncertain. On the other hand, Dr. Slow Play and Sniper Eye move down. As you can see, they move down, but not as much because their skill is more tested with time. So this process can be succinctly represented by the probabilistic program shown to the right, which computes the skills for the players having observed their performances in the game. I'll get into the details of what this program actually does later in the talk. So here is the syntax for a simple probabilistic programming language. As I mentioned before, the part marked in red, the probabilistic assignment and observed statements, differentiates this language from a regular programming language. And the meaning of a probabilistic program, as I mentioned before, is the probability distribution over its output states. I've been quite informal about this notion, and the seminal paper by Dexter Cozen was the first to formalize the semantics of a probabilistic program. I've also listed some other recent papers on this topic that might be of interest to some of you. So we've seen that a probabilistic program implicitly specifies a probability distribution, and inference is the process of efficiently estimating this implicit distribution specified by a probabilistic program. So here is the probabilistic programming landscape. There are a number of probabilistic programming tools, both from academia and industry. And recently, DARPA announced a $48 million initiative called Probabilistic Programming for Advanced Machine Learning. And this has also sparked a lot of interest in both the programming languages as well as the machine learning communities. Most of these tools use programs as a succinct and convenient means to represent a probabilistic model, but do not necessarily exploit the structure or semantics of the probabilistic program in order to perform inference. So at Microsoft Research, we built a probabilistic programming system called R2. And here are the features of R2. So R2 uses program analysis techniques combined with MCMC sampling in order to efficiently perform inference. It also employs theorem proving technology in its engine. R2 implements provably correct inference algorithms. In other words, we're able to formally show that the results of inference are consistent with the semantics of the input probabilistic program. And it is also available for download, and I have given the link over here. So, like I mentioned, program analysis can be used in a number of ways to perform inference, and here are a couple of references on this topic. But today I will show you how efficient sampling can be performed using ideas from program analysis. So let me illustrate the main idea with the help of an example. So imagine you are at work and you get a phone call from your neighbor and she tells you that your burglar alarm is on. We would like to determine the probability of a burglary, and this depends on factors such as the occurrence of an earthquake, whether the phone is working or not, and so on. So these dependencies are specified by the probabilistic program in this slide. As you can see, it's a fairly simple program, but it has lots of events and which are conditioned on other events. And we'd like to estimate, and the meaning of this probabilistic program is the probability distribution over the return expression, which is the probability of burglary. and we like to estimate this probability. So one way to estimate the probability of a burglary is to run the program multiple times, collect the samples, and estimate the fraction of times burglary equals true versus the total number of samples collected. Unfortunately, this is quite hard to do, as the probability of satisfying the observed condition, which is probability of a phone call, is quite low, which means that most of the runs of the program will not succeed and silently terminate, as they will not satisfy the observed statement. And this is important because we are only interested in computing the probability of a burglary under the assumption that a phone call was made. And this phenomenon is very similar to what happens when one does rejection sampling. So when you sample under constraints, one tends to reject all samples that do not satisfy the constraints that are of interest. So essentially, to perform efficient inference, we would want to ensure that the samples drawn from probabilistic assignment statements eventually lead to program states that satisfy the observed statement. So the main idea or the main objective is to avoid these rejected runs so that we can do efficient inference. And the main idea that we have is to hoist conditions in observations to probabilistic assignment statements and sample from the resulting conditional distributions. So what do I mean by this? Let me illustrate this with an example. So what we do is we take the given probabilistic program and use a transformation called the pre-transformation to obtain the following new program. This program is interesting because, as you would notice, it has observed statements after every probabilistic assignment statement. So the interesting thing about the transform program is that it is semantically equivalent to the original program. Furthermore, if we sample from each probabilistic assignment statement in the transform program, conditioned on the observation immediately following it, we can guarantee that there will be no rejected runs. In other words, the samples are such that the observation that a phone call is made is always satisfied. The next question is, how does one compute these observed conditions? So we use a very well-known idea from program verification, which is Dijkstra's precondition, to do this. Essentially, what this operation does is to propagate the observed condition backwards through the statements in the program, such that satisfying those propagated conditions would ensure that the observer is satisfied. And the rules in this table precisely describe how to perform this operation. So the rules over here are quite standard, and the new rules for probabilistic programs are shown in red. So these are rules just for the probabilistic assignment statement and the observed statement. So just to illustrate this, let's say you have a condition which is x plus y greater than 5, which you'd like to satisfy after executing a statement x equals 3, which is the annotation on the edge over here. The question that the weakest precondition tries to answer is, what is the condition that must be true in the upper cloud such that upon executing the statement x equals 3, we are guaranteed to satisfy the condition x plus y greater than 5. So using the Dijkstra's weakest precondition, we get the condition y greater than 2. What this means is that starting with any program state satisfying the condition y greater than 2, if we were to execute the statement x equals 3, the resulting state will definitely satisfy the condition x plus y greater than 5. So what does this translate to for our probabilistic program? Let me illustrate this for a path in the burglar example program. So the statements to the left of the table represents a path in the original probabilistic program. And let's say we start with the second last statement in this trace. In order to satisfy the observed statement here in the second last statement, we need to satisfy the predicate called. And that's exactly what is shown in the column to the right. And next, going back one more statement, in order to satisfy the predicate or condition Mary wakes and phone working, in order to satisfy called, we need to satisfy the predicate Mary wakes and phone working. So this process continues in a backward fashion to generate the preconditions, which are all shown in the left column. And these are exactly the conditions used to generate the observed statements after every probabilistic assignment statement in the transformation. So in order to safely apply this transformation, we need to formally show that the probability distribution specified by the program P is the same as the distribution specified by the transformed program P of P. And this is exactly what we show in a recent AAAI paper. As I mentioned before, in order to sample efficiently from the transformed program, we need to draw samples from truncated distributions. And these truncated distributions are nothing but the distribution in the probabilistic assignment statement conditioned by the observation immediately following it. What we are also able to formally prove is that this sampling process, which runs the program such that you sample every probabilistic assignment statement with a condition, produces the same estimates as a rejection sampler. And furthermore, since there are no rejections, we are able to show empirically that our sampling process is very efficient. So that was one instance of how to use ideas from program analysis to do efficient inference for probabilistic programs. And there are many interesting and exciting applications for probabilistic programming, and in a number of diverse domains. In the next part of the talk, I will describe a new application which is about using probabilistic programming for debugging machine learning tasks. Specifically, we will look at machine learning tasks such as classification, where the objective is to learn a classifier or function from training data that is able to distinguish positive examples from negative examples. So assume we have a user who's unhappy with an outcome of some classification. And we are interested in finding errors in the examples of the training data that are responsible for the undesired outcome. So let me illustrate this better with the help of an example. So assume we have this set of images where we'd like to learn a classifier or a function that is able to separate or distinguish vehicles from animals. Let us also assume that this dataset has errors where the region shown marked in red is a set of small cars that have been erroneously labeled as animals. Consequently, the learning algorithm learns this curve H noisy that separates the positive examples from the negative examples. But the problem with this learned function is that given a new image of a car, it incorrectly classifies it as an animal. So our objective is to fix errors based on user feedback on this incorrect classification and learn a new classifier hclean that correctly classifies the new car. So how do we do this? So one possible method for isolating these data errors is program slicing. So what you would do is start with the error, tracing backwards through various program dependencies to find out which parts of the training set affect it. Unfortunately, this does not help as the computation of H or the classifier depends on all points in the training set gamma. Another approach is to experiment and pick a set of training points, flip their labels, and retrain with the hope of removing the error. The problem with this is that there are just too many subsets to flip. And retraining for every subset is also very expensive. So therefore, the question we ask is if there is a systematic yet efficient way to perform this experiment. So before I describe our technique, let me formally define a machine learning or ML task. A machine learning task is a tuple consisting of gamma, delta, and A, where gamma is a training set of examples, delta is a test set, which is an evaluation set, and A is the training algorithm. And the figure on the left is a two-stage design flow of a machine learning task. there is a training phase in which the machine learning algorithm A is applied to the training set gamma to learn a classifier H. And there's an evaluation phase which is used to judge the quality of H on the test set delta. So in our setting, we're given a machine learning task, and the user is unhappy with some outcome phi of H over the learned classifier. For instance, phi of H could be a misclassification over some point xi, yi in the test set delta. And the objective of the debugging tool is to measure the possibility of each training point being the root cause for unhappiness, which is phi of H. So our main idea is to use Judea-Pearl's notion of causality to root cause data errors. So let the y sub i's be a set of binary valued inputs, and let O be an output binary variable which is computed by applying a function f to the inputs. And let O equals little o be obtained by applying f on the little yi's. What we're interested in is computing the probability of each input value, the little yi, causing a particular little o. And this probability is called the probability of sufficiency, or PS score, for the ith input y sub I. So let me try to explain this with some pictures. So let's assume that we start in a state where the output capital O has value little o, and the input y sub I has value little y sub I. This is precisely the blue region in the picture. In other words, both the input y sub I and O have different values than the state we're actually interested in. Now, if we were to flip the value of the input y sub I to plus little y sub I, that is, restore its value to the value of interest, then either the output O remains the same, shown by the blue region below in the figure, or it flips and its value is restored to the value in the current state, and this is shown by the dashed region in the figure. So the probability of sufficiency, or PS score, is given by the probability of entering the dashed region. So the intuition is that if the probability of entering the dashed region is high, then we'd like to believe that the ith label is indeed the root cause for the error. What's the connection to probabilistic programming? So here is a probabilistic program that computes the PS score for the ith label. So this program takes three inputs: the training algorithm A, the training set gamma, and the error predicate phi as input. And essentially what this program does is exactly encodes the PS computation that I described earlier using the picture. Specifically, what we want to do is to compute the probability that the ith training label in the training set is a cause for the error predicate phi. So what this program does is that in line 1, it samples a set of labels from the training set, subject to the condition that the ith label has a value that is different from the current state, and this is encoded via the observe statement in line 2. Next, we learn a new classifier H from the new training set in line 3, subject to the observe condition on line 4, which insists that the learned classifier does not satisfy the error predicate. Now, upon restoring the value of the ith label in line 5 and retraining on line 6, the return expression encodes the probability that the error predicate is satisfied. In other words, inference over this program will compute the PS score for the ith label, or assign a score which basically says how likely it is that the ith label in the training set is responsible for the error. Unfortunately, inference on this probabilistic program is easier said than done, as there are a number of challenges. So let me go through these challenges. First, to obtain a reasonable estimate of PS, we potentially need to consider all subsets of a large number n of training points. Even for modest machine learning tasks, n is typically greater than 1000. Second, inference needs to be performed once for each label y sub I, where the number of training labels can be really large. And finally, for each subset of training points, inference needs to be performed over the actual implementation of the training algorithm A. This is usually highly optimized C++ code, usually several hundred lines, and is beyond the scalability of any existing sampling technique for probabilistic inference. So how do we handle these challenges? To handle the first challenge, we assume that that a very small fraction of the labels in the training set are corrupted. In other words, we assume that the training set is by and large okay. This is a reasonable assumption because we'd like to believe that the errors are rare and not frequent, and the training set is by and large okay. So therefore, in statement number 1, we sample the training labels from a prior, which basically ensures that large perturbations to the training set have a very low probability, which basically says that there's a heavy bias towards the training set gamma. To handle the second challenge, we perform a program transformation where the part on the top, the program that you see on the top, is not dependent on label I, which means that we can reuse samples across labels, and this improves efficiency. And the program fragment in the bottom part of the slide is specific to a particular label, and each of these programs can be run in parallel. And it turns out that it can be formally shown that if you do this partitioning, the results that you would get by running an inefficient sequential version would be exactly the same as running this efficient parallel version. Finally, to handle the learning algorithm, we approximate the learning algorithm A with A hat, which is a simpler model of A. In particular, what we've done is to design gray box models for a number of machine learning algorithms over which inference can be performed very efficiently. So we've carefully looked at implementations of logistic regression, boosted decision trees, and so on, popular machine learning algorithms, and designed gray box models over which inference can be performed very efficiently. So there are some more details, and we hope to make our details and implementation available soon. So we've implemented these techniques in a debugging tool which we call SI, and evaluated it on a number of data sets. So SI essentially takes a machine learning task as input, together with the errors or the causes for unhappiness by the user, and produces root causes or training labels as output. We use this information to fix the training set and measure the improvement on the resulting learned function. That's how we evaluate how useful the root causes are. So we evaluated Psi on 2 data sets, sentiment and income. Sentiment is an IMDb movie review data set that is used for sentiment analysis, and income is a benchmark data set from the UCI machine learning repository that is used to predict income levels based on census data. Let me quickly explain results for a particular table. So let's focus on the row sentiment 1 in the table logistic regression, in the table for logistic regression. These are the results when logistic regression is used for classification. For this benchmark, Psi is able to recover 90% of the errors in the data set or in the training set, and the sequence of numbers in the test error column for this row are as follows. What they mean is that without the noise or errors in the training set, the test error is 16%. After introducing the errors, the test error increases to 19%. And then upon running Psi and fixing the errors, the test error goes down again to 17%. As you can see, Psi is quite efficient and takes 55 seconds for this particular row to identify the erroneous labels in the training set. So in summary, we think that there is a huge opportunity for building productivity tools for machine learning tasks. I've shown you how probabilistic programming can be used for debugging errors in the data. As you can imagine, there are several other ways in which machine learning tasks can produce incorrect results. These can occur due to errors in the feature values, due to over and underfitting issues, incorrect parameters to the machine learning algorithm, and so on. On a side note, it would also be interesting to figure out how to perform systematic testing, which is used for regular applications for these machine learning tasks. Another opportunity for tools is to automatically synthesize probabilistic programs, and that is the next topic that I will discuss. So here's the probabilistic program for the skill rating system TrueSkill that I described earlier. As you can see, if you look at this program, while understanding the probabilistic program is presumably relatively easy, writing good probabilistic programs seems to require some expertise in probability theory and probabilistic modeling. These are skills which a typical programmer usually doesn't have. For instance, in this TrueSkill program, the skill is sampled from a Gaussian prior in line 4, and lines 6 to 10 say that the performance of a player is a noisy measurement of a skill. And line number 9 says that the outcome of a game depends on player performances. So essentially what this means is that this indirect dependence of a game on the skill takes into account games where a player with higher skill can lose to a player with a lower skill on a bad day. So for example, perhaps there's a player who plays who has a high skill, and that player loses to a lower skill because of a headache or some bad day and so on and so forth. And this indirection where the results of the game depend on the performance, which is a function of the skill, allows us to have that flexibility. On the other hand, an inexperienced programmer may replace these lines 7 to 9 in TrueSkill with the simpler assignment which directly says that the result of a game is directly equal to the fact that the skill of that player. So player 1 wins the game if the skill of player 1 is greater than the skill of player 2. However, such a program, as I have described, constrains the skills of the player more than what we would like to. So the question we ask is whether one can automatically synthesize a probabilistic program from examples of data. It turns out that program synthesis from scratch is extremely hard. That said, we don't necessarily have to start from scratch, as programmers usually do have some design intuitions that one can build on. So an interesting question is whether a programmer, whether we can have a programmer specify only a sketch of a program and then synthesize the program automatically. This is what is usually done for synthesis of deterministic programs, and it's been quite successfully applied in a variety of situations and domains. For instance, in the case of TrueSkill, let's say the programmer has an intuition that the player's skill is defined based on some prior estimates, and the results of the game depends on the skill of the players who are playing it. Then the programmer can specify her intuition by a sketch as shown in the slide. Notice that this sketch specifies only the deterministic components of the probabilistic program, and the probabilistic components are holes indicated by question marks. So with the first question mark, the programmer conveys the intuition that the skill has a value that does not depend on any other variable in the program. With the second question mark, the programmer conveys the intuition that the result of a game depends on the respective skills of the players participating in the game. The tables to the right are instances of data which convey the intuition about the skills after a set of games has been played. So for example, in the top table, the first row basically says that in game 0, player 0 plays player 1 and player 0 wins. The second row says that in game 1, player 1 plays player 2 and player 1 wins. And in row 3, or in game 2, player 0 plays player 2 and player 0 wins. And the table below that basically are the skills after playing these 3 games. Since player 0 won both games, player 0 has the highest score. Player 1 just wins 1 game, so she has the next highest score, and so on. So we're given this data which basically conveys the fact that the person who wins the most is likely to have the highest skill. And the question is, given this data, can we somehow synthesize probabilistic fragments possibly for these question marks. So more formally, we're given a sketch which is which we denote by the symbol P brackets with a dot in it. And the synthesis task is to find the right instantiation for the whole in the sketch. In other words, we are interested in finding a completion to the program or a completion to the sketch which has the highest likelihood of generating the data D. So essentially what this expression is saying is that fill the question marks with program fragments such that the probability of generating the given data is maximized. And once again, there are a number of challenges. And one primary challenge is that given a sketch, the number of completions for that sketch is possibly unbounded. So finding completions to a sketch is really hard as the number of completions is unbounded. And I won't get into details of how we tackle this, but essentially what we do is that we efficiently explore the search space using Markov chain Monte Carlo techniques, which offers an intelligent way to explore a search space. Furthermore, even if we use sampling to sample various programs, for each candidate that we choose, for each candidate completion, the computation of the likelihood score is expensive. So remember, we'd like to choose a program that maximizes the probability of generating the data, which means that for every candidate that we generate in our search, we need to compute a score as to how good that candidate is with respect to the data. So let's look at a simple example to understand why the estimation of this likelihood is expensive. So consider the following sketch and a completion. We would like to compute the likelihood score for the completion, and that's given by this density D given P of H. So this is equivalent to computing the density for the event x1 plus x2 equals k, which is analytically given by the integral shown in the slide. Therefore, in order to estimate the likelihood score, we need to efficiently estimate these indefinite integrals. And computing these integrals is usually very expensive. So in our experiments, initially we tried to exactly estimate these integrals using numerical techniques. And we observed that we were able to generate only a few tens of samples or programs in 100 seconds. And this renders the search or the MCMC search to be highly ineffective. What we like to do is to quickly compute the scores so that we can generate, tens of thousands of programs in a second, in a few seconds. So in order to tackle this issue, we symbolically compute the likelihood by approximating complex continuous distributions using a family of simple distributions. Essentially what we do is we choose this family of mixture of Gaussians or MOG, and these have this universal property which guarantees that they are able to provide a reasonable approximation to a number of continuous functions. So going back to the TrueSkill program, to compute its likelihood score with respect to the data, what our technique does is to make a pass of the program line by line. And during the pass, we maintain a symbolic state for the likelihoods. We populate a map from every variable to its approximate likelihood expression. For instance, when we encounter the variable skills of I, its corresponding entry in the table is updated to its MOG or mixture of Gaussian approximation to likelihood. Note that estimating this likelihood for the random variable R of g.id would typically involve the estimation of complex integrals, such as estimating the density of perf1 greater than perf2 and so on. And using the MOG approximation as shown in the table, we can very efficiently and symbolically estimate the likelihood score. So we've implemented again this synthesis algorithm in a tool called psketch. And in our evaluation, we had the following goals. So the questions we asked was, what is the speed up due to MOG approximations? How well does the distribution of the synthesized probabilistic program match the actual distribution? And we also asked the question of whether psketch is able to synthesize interesting probabilistic programs. So we evaluate the effectiveness of the approximations for computing these likelihoods by comparing the number of sample programs that we're able to generate per 100 seconds with and without the approximation. And as you can see from the chart, the approximation allows our tool to generate many more programs than the exact approach. And let me also say a few words about our benchmarks. So TrueSkill is the skill rating system, which is a variant of the example which I described. Burglary is Perl's burglary example, which you've also seen. The click-through benchmarks mainly consist of programs which model how the relevance and appeal of links in a web search result affect which links the user examines and clicks on. Conference models the accept or reject decision of a paper based on the quality of the paper, the expertise of the reviewer, and a possible error made while reviewing the submission. Clinical models a lab setting where the effectiveness of a drug is inferred by observing its performance on a control and placebo group. And for each probabilistic programming benchmark, what we did was to generate data sets by running the program multiple times and collecting the outputs generated. And we also wrote the sketches for the benchmarks by replacing parts of the program that involved probabilistic reasoning with holes. So that describes our experimental setup. So in order to evaluate how well the distribution of the synthesized program matches with the intended distribution, for this purpose, what we did was we computed the posterior distributions on the skill. So we took TrueSkill and for 3 players, and we computed posterior distributions on skill variables for 3 particular players and measured how they compared with the analytically computed skill values. As you can see, we compared the marginal distributions of the skill variables for the original program, the synthesized program. And from the plots, you can see that the synthesized program approximates the actual analytically computed values very well. So that's given. So the approximation is given by the histogram, and the analytically computed curve is shown by the curve in the plot. In order to demonstrate the efficiency of our algorithm, we ran it on sketches. We ran it on a number of benchmarks, and the inputs were the sketches together with the generated data sets. And as you can see, it can be observed that psketch takes time in minutes and often sometimes in seconds to synthesize a program from its sketch and data. So to summarize, we've seen that probabilistic programs are succinct ways of specifying probabilistic models. There are a number of diverse applications in machine learning, biology, security, and so on. And I've shown you another application, which is debugging machine learning tasks. As far as solving techniques is concerned, what we have observed is that probabilistic inference is very similar to program analysis, which means that the probabilistic inference is a new application for many well-known techniques in program analysis and software engineering. We think this is a great opportunity for building a programming environment for machine learning. For example, a compiler or a runtime for use by experts with domain knowledge but lack machine learning expertise. And as I've shown, there are several directions for future work. With that, I'll stop. Thank you.
Thank you, Dr. Nori. Our first question is asking, can you comment on this work in relation to some AI methods, specifically those that are using fuzzy logic? For example, fuzzy logic was successfully used recently to control ill-defined processes like cement making.
Mm-hmm. Right. So I guess they are related in the sense that essentially what we're saying with this work is that we're focusing on the fact that you can specify systems which need to naturally take into account noise with the help of programs. So it could well be the case that you could write up a probabilistic program which specifies the problem and also inherently takes into account noise, and the solving technique could well use techniques from fuzzy logic. What we've done in our work is to sort of exploit the semantics of the program and solve the program using probabilistic program using program analysis techniques. But there are other probabilistic programming tools which, for example, reduce the probabilistic program to a well-known abstraction from machine learning, for example, a graphical model, and solve them.
Thank you. Our next question is asking, you spoke of synthesizing the probabilistic portions of the programs. Doesn't it make sense to pair programmers with statisticians or data scientists and then have the latter fill in the probabilistic portions of the program instead of automatically synthesizing an approximated distribution?
That's a good point. In fact, when working on this project, our hope was that we would help both. So our hope was that a domain expert, be it a regular programmer or a statistician, would actually specify dependencies using the sketch, which are deterministic dependencies, and our tool would actually automatically synthesize portions of the program which are probabilistic, which are most consistent with the data. I think it still requires a lot of expertise to come up with a sketch, because in fact, as you would have noticed, our experiments were very synthetic in the sense that we took all these probabilistic programs from various papers where people actually put in a lot of effort to carefully design probabilistic models, and we wiped out the probabilistic components of those models and then tried to see if we could synthesize back those components that we removed. But it turns out that where statisticians would come in is to work with domain experts to actually come up with reasonable sketches, because the probabilistic fragment, including the parameters and so on and so forth, really depend on the data.
Okay. It seems that probabilistic programming is currently a well-studied area. What are some of the key unsolved problems that are perhaps preventing many people from applying these probabilistic programming techniques in their everyday work?
Right. So that's a good question. So one of the probabilistic programming is very nice because it allows you to, in a scientific way, actually write a probabilistic model and so on. So one problem is that, for example, let's say one problem that I find is that, let's say you want to do something like regression, which is curve fitting or maybe classification. It turns out that if you were to use state-of-the-art machine learning techniques that are based on optimization, even though they are approximate, these techniques scale way better than Bayesian techniques, which form the backbone of probabilistic programming solvers. So one problem, while the programs seem very intuitive to write and so on, I think one problem is about scalability. And the other one is, of course, expressiveness, in the sense that you are right in that it is quite popular, but the programs the kinds of tasks that you can write using probabilistic programs are quite limited. And an interesting problem is how to sort of integrate a probabilistic programming language into a regular language. So, for example, if you'd like to seamlessly use probabilistic programming as part of your everyday programming language, it isn't clear how one does that. So I think these are the sort of the roadblocks for wide adoption.
All right, thank you very much. I'm afraid we've run out of time today. I would like to thank Dr. Nori once again for his informative presentation and insightful answers to these several questions. Special thanks to each of you for taking the time to attend our webinar. This webinar was recorded and will be available online in a few days at www.sigsoft.org/resources/webinars.html. You can find announcements on upcoming ACM and SIGSOFT webinars and other ACM activities at learning.acm.org and at www.sigsoft.org. That said, this is Robert Dyer saying goodbye for now. Thanks again for joining us, and I hope you will join us again in the future.